this presentation is actually broken different parts, at least like 3 different parts. So I will be giving an introduction about what is ARD and why we need to have ARD, and then I'll be followed by Pete, also from here from Maxar, and he'll be talking more on about the aspects of how do we generate those products, and he will go more in details about, for example, orthorectification alignments, and then after your lunch, we will have a demo where we'll show how you can apply ARD to a, for example, a machine learning framework. So I'll just start. I see everyone is sitting down now. So, okay, so what is ARD? First of all, there are multiple different definitions of ARD. I want to put that out just because if you hear a presentation from NASA or ESA or CEOS or IEEE, there are many different definitions. And so I will be talking about what we at Maxar call ARD. And I'll give you like some introduction to all the building blocks of what is an analysis-ready data product. In general, why do we need it? Well, we need something, in this case, as a framework that allow us to analyze the data and extract the data in a much faster way. And so you can think about ARD as a workflow that is designed to allow users to extract information from pixel in a much faster way. And it generally is built on top of different building blocks that can include, for example, atmospheric compensation, orthorectification, pansharpening, color balancing, bundle block adjustment, and grid alignment. The nice thing about this is that you can think about ARD as a standard, for example, where you have all your pre-processing that are done on the ground by, for example, Maxar or ESA or NASA, so that a user doesn't need to do them. For example, when you work with satellite data, one thing that you generally want to do is to work in a physical space like TOA reflectance or surface reflectance. And so you need to have some sort of atmospheric compensation. Generally, you don't know how to do that. You don't know what the atmospheric conditions are. And so that single task might require many hours of your time that can be better spent analyzing the data rather than massaging the pixels. This is more or less why we have, why the industry, but also like governments, again, NASA and ESA are front runner on this, why we need to have like a stack of information is generated on a common standard. So this is just a nice illustration where I'm trying to explain the importance of latency. So when you place a tasking order and the image gets collected, it might take about like an hour, more or less, between collection, the downlink to the ground stations, the generation of the data and the delivery to an FTP on S3 buckets. Sometimes for special orders, it might take in the order of a few minutes from collection to delivery. Some other times can take a few hours, but in the bulk part is about like an hour. But then once you have the data, and specifically when you have the bottom one of this animation, like this image here. So how do you extract 3D information? How do you extract building footprint? How do you extract roads? How do you put all that together in a 3D environment? All that is the pre-processing that doesn't really involve ARD. This is something that you as an end user want to do. But before you get to the point, you need to have, for example, a stack of images aligned and register, it's color consistent, and all the other nice pre-processing that are done for you. And this is really difficult. And so I will briefly touch on why not the images are created equal. And I'll try to dive more into this agility of the satellite, the different bands, and the various effect of the atmosphere. And as I say, Pete and Manny later, they will be talking about how do you put that together, and how do you create a framework to do machine learning, for example? And just to give an idea, more or less ARD involves those two pieces at the end, where a bunch of pre-processing is applied and then the image is delivered somewhere for the user. Before I go ahead with the slides, I really would like this to be interactive. So if you guys have any questions, I don't want you to raise your hand because I cannot see you, but please get a microphone and interrupt me, ask me questions. I think this is a lot better. It's a much better interaction. So if you have any questions, just let me know. So let me dive a little bit why not images are created equal. And I'll do this, again, this is a Maxar-centric presentation, so I'll be talking about Maxar, but this generally applies to any other provider. Again, NASA with Landsat or ESA with the Sentinels and any other commercial providers. In general, we have older satellites like Econos and QuickBird that have been retired now. We have 4 satellites that are currently orbiting and collecting data, the WorldView 1, 2, and 3, and GeoEye-1. And we are producing, we're assembling 6 more satellites called WorldView Legion. We'll be launching those satellites in the next few months. And this new satellite will allow us to increase the revisit time by 15 times per day. So we will be able to image the same spot on Earth 15 times from morning to afternoon. And this will, the Legion will be a 30 centimeter class satellites. And the nice thing about those satellites, and I have some specs here, is that they're not all sun-synchronous orbits. So they don't just go across the polar orbits, but also like mid-inclinations. So this will allow the Legions to revisit the same spot on Earth at different times through the day. Another nice aspect is that it is still an 8-band satellite, but we dropped the near-infrared 2 band that characterized the WorldView 2 and 3 satellites, and we favor much narrower bands in the red edge part of the spectra, and this will allow much better precision ag studies. And you can see those bands are much narrower compared to the other one. Those are the two main things I would like to point out. And again, the revisit. This is just a simulation that we've done. You can see, South America, North America, Europe, Northern China. You can get up to like 15 revisits per day. That's really important because now we're going to be collecting different time of the day from many different directions, and the illumination will be different, illumination of the sun. And so if we don't normalize the images in a consistent way, it will be really difficult for users to just get an image and apply their models, for example. So I believe that in the rest of this school, you guys will hear an expert about hyperspectral. So I'm not gonna dive too much into why it's really important to have multiple bands. I think that's pretty trivial, but you can see things that generally might not be easy to see with the naked eye. But one thing I would like to point out is that, as I say, different satellites have different bands and band pass filters. For example, this is the spectral band of the panchromatic image of, I believe, QuickBird. And you can see there's a blue band, a green band, and then there's a gap here, and then there's a red band, and the near-infrared band. And the WorldView 2 and 3 have 8 bands, where some of those gaps here in between green and red are filled with a yellow band, and there's a red edge band. But bottom line, what happened is that the human eye can see colors mostly in the blue, green, and red, but there are also like secondary lobes in other parts of the spectra. And so depending on the number of bands that your satellite have, you can see colors in a different way. For example, I don't know how this is rendering on your side, but this is really dark red, and this is really bright red to me. This is more like a sand color compared to bright yellow. And so if you don't accurately represent colors, it's going to be really, really difficult to have a consistent time series across different images. So when you work with different bands and band passes, you need to make sure that color consistency is achieved. Spatial resolution also is it's really important. Those are images that are simulated from 30 centimeter 30 centimeter images. And you can see the larger the GSD, the lower the resolution, and you start missing out fine details. For example, here and here, you cannot really see there are some utility vehicles that you can see only in the 50 and 30 centimeter class sensors. And this is really important when your satellite are very agile, so they can shift from left to right, front and back, and they can collect images at different viewing angles. Why is that important? Because the more you are off nadir, the larger is the GSD. So for example, let's say that Legion or Worldview 3 is, for example, 30 centimeter satellite and nadir. If you're off nadir and you're looking, for example, let's say around 50 centimeter, 45 centimeter, 45 degrees, your GSD will be double. And so you're now looking at satellite or an image is collecting about 60 centimeter resolution. And if you're 60 degrees off nadir, then your image will be 4 times the initial resolution. So we're talking about a meter 0.2. And so all these really changes what you actually see. So this is an image that we acquired at 7 centimeter resolution, and we slowly degraded to 60 centimeter. And you can see at 60 centimeter, you cannot even understand this is a car. Even at 50, it's really, really difficult. And you cannot discriminate, for example, the windshield or the back part of the car. And to me, this is like I don't know, maybe it's a trash can with a scooter. I really cannot tell what I'm looking at. So trying to train models on those type of images, it's really difficult. And especially if you train your model, for example, on a 30 centimeter image like this one, your model will not port very, very easily in this condition. And we actually did an experiment where we used still those aerial images, and we did a simulation of different GSDs. And what you can see is that, and we did a car counting. Car count is one of the probably easiest examples that you can do using satellite images. There are a ton of cars, so you can get a lot of training data. And what you can see here is that there is a pretty big degradation going from 7 centimeter aerial image where we achieve about, I think it was 92, 93 F1 score, compared to a 60 centimeter collection, where we barely made it to 55 in F1. So it really depends on what is your collection angle and what is the GSD of your sensor that you're using. And so that was a simulation done on an aerial image. We have done pretty much the same experiment using Worldview 3. And you can see that there is a pretty big drop of accuracy going from 30 centimeter where when we were able to count about 1,500 cars to only 1,200 cars to only 31 cars at 60 centimeter. So it's really important you understand the geometry of your collection and what you're able to resolve with that type of data. Geolocation is also really important. You can think about geolocation as how accurate your pixel is on the grid. So let's say that, for example, you're driving and you're downtown and there are a bunch of roads next to each other, and your GPS, like Google Maps, tells you, hey, turn right here. But you're right here, there is a wall, and the road is actually 100 meters later. that is where geolocation is important, to really map the right pixel in the right place on Earth. And I know that Pete has a lot of really cool animation about this later. Agility is also a pretty big challenge, not only for the GSD, but also the perspective that you collect. And so this was an image that was collected, don't remember, I think it was like 50, 60 degrees of nadir. And so you can see that we can, this is almost like if you're on an airplane, you can see the all the Washington Mall here, the house, the Pentagon here, and the perspective is not what you generally expect from a satellite image that you're looking at nadir. And this kind of situation is actually really, really common when you have something is not usual. Like, for example, you have disaster, you have to, you have to collect a bunch of images from completely different direction, whatever they are, because it's important that you collect something. And this is not really probably the prime example, but last week with the funeral of the Queen, we collect a ton of data in London, and you can see we were able to collect multiple images on the day of the funeral from 1142 with WorldView 3, 1144 with WorldView 2, 1237 with GeoEye-1, and WorldView 1 at 2 o'clock in the afternoon. And you can see that the perspective of those images are completely different. One is looking, those two are looking, I believe, from the south, and this is looking from west, and also this one. So you need to be able to understand the geometry of your collection and how you can put that on a grid. Oops. And again, why? Why? Because we are going to collect a lot more data than in the past. And when I say we, I mean the entire industry, the all government agencies. The amount of data that we are producing every day, it hasn't been seen before. And this will really enable a much, much better, more accurate, comprehensive analysis of the pattern of life and human geography. But you need to have some sort of consistency of your data. Otherwise, you're not going to be able to put anything on a grid that is meaningful, and you will spend most of your day trying to move and shift the pixel to fit a model. Let me then dive a little bit more into what is ARD and for you as a user. So you can think about ARD as a stack of images, and you don't need to get the entire collection. For example, if you're looking just at Buckingham Palace, you can just get the tile over, over the central London. You don't need to get the whole thing. And you can get a deep stack of images that were collected, I don't know, from 2005 up to yesterday, if you want, or today. And you can put all that in a cube of data stack. And this allows generally like a faster processing, because you don't need to, get the data, orthorectify, pansharpen for yourself, color adjust it. Everything is done for you before the data is delivered to you. And this also lowers like storage costs. Again, you don't need to have like 10 scenes that weigh, the size of, 10 gigabyte each. You can only have your tile, which is a lot more efficient. And as I said earlier, like there are many different definitions of what is an ARD product. For us, we can, we can see an ARD product, something is going at least through atmospheric compensation. The data is orthorectified, aligned, and optimized for cloud computing. And there are, metadata and masks that are associated with the tile that you are looking at. And again, every provider of data has a slightly different definition of ARD. So don't get stuck on these, 5, 6 items, but those are the main building blocks that you should expect to receive. I'll dive a little bit more into the spectral part, the atmospheric compensation part, and Pete will go through some of those in the next time slot. Before we talk about atmospheric compensation, we need to make sure that the satellites are calibrated. And we do this in many different ways. In general, one way to check if your satellite is calibrated is you do some measurements on the ground, and those measurements can be in a desert where everything is very uniform and bright, or you can use, for example, tarps. This is our calibration facility here in Colorado, where we have different tarps with different brightness. And then once you have the measurements on the ground, you also need the measurement of the atmospheric parameters. Once you have those two, you project your measurements on the ground up to the sensor using radiative transfer models, for example, like Modron or 6S. And sometimes you can inject some BRDF. BRDF is the bidirectional reflected distribution function, which is basically if you're looking from different directions, your object is brighter or darker. For example, if you're driving at sunset, you can see that the highway is generally much, much brighter because the sun is reflecting on it. So that's what BRDF is. Once you do your radiative transfer modeling, then you know what the prediction of those radiances on the ground should be, and you compare them to what the sensor sees. And if they're not the same, it means that the satellite is not accurate. And so you do the calibration of the satellite. Obviously, this is assuming that your instrument on the ground, either the spectrometer or the sun photometer, are accurate. Otherwise, you're not doing a good job. So once you have measurements on the ground of a dark tarp, for example, this one, and something bright like this one, and something somewhere in the middle like this gray one, you can do like an interpolation. And this interpolation can be as easy as a linear interpolation or something fancier if your sensor is very nonlinear. But basically, what you want to get is some regression like this one, where you can correct your pixels for the right values. And generally, you do this at least every few months, so that you're sure that your sensor is calibrated through time. And you also compare, what we measure against what Landsat, for example, measures, or for example, Sentinel. The resolution are not exactly the same, the spatial resolution, so it's a little bit difficult to compare apples to apples, but you want to be somewhere in the ballpark. If you are within like plus or minus 5%, you're probably okay. Again, Landsat and Sentinel only look at nadir, whereas we have agile satellites, so you also need to account for BRDF and a much longer path radiance. So again, 5% is generally a good target to have. Once you have an accurate satellite, I don't know if Paolo Gamba is online, but I pick an image over Cremona in Italy, northern Italy, where there is generally a lot of fog over there. And so I pick that as an example where it's really, really important to extract the right value information from the ground, removing all the effects of the atmosphere. And you can see this is like A's basically. Here on the Alps, there is a lot less atmospheric scattering. And the southern you go, especially around here, around this cloud, you can see the effects of the atmosphere were predominant. And so this is very nonlinear. You cannot just say, hey, I want to remove X% of atmospheric component. You actually need to do this on a pixel basis. And if you apply atmospheric compensation, then you get something like this, where the green color over here, it's the same value of green over here and over here. And so you want to be consistent through the image. But you also want to make sure that not only your satellite is calibrated, but also that the surface reflectance product that you generate is calibrated, so that you can have a three-way system where each of those components is calibrated against each other. And so to define and to measure our spectral accuracy, We also go again in different parts of the US, for example, for this campaign, where we measure different targets. And those targets were, for example, asphalt or tarp material, concrete, sand. And we took a bunch of like BRDF measurements. Those are what those are. And what we did was to then get a time series over that target and see the stability of this thing up through time. And this is what more or less those plots are showing, where I believe those were a different color of tarps. This was a green tarp. You can see the green band here. This also was a green tarp, but it was like darker. This was a blue basketball field. And this was something really dark, like a black tarp of the running track. And those were concrete. And what you can see is that not only the data is very consistent, but it's also very, very accurate. So just this part about surface reflectance takes generally multiple years of research to get to that point. And this is just one of the components of ARD. This is another one. And I don't know if the animation is coming clear there, but what we did was to put together, again, a bunch of scenes where we did the orthorectification, and we did the orthorectification and alignment. And Pete will go in much more detail on this topic after me. But what I want to show is that this point moves a lot. Even if you did a careful orthorectification, there is still a shift. And even after the alignment, you can see that this pixel doesn't move anymore, but all the buildings move. And the reason why they move is because you're viewing them from different angles. And so the projection of tall building is in a completely different direction depending on where you're looking from. So not only there are issues with the orthorectification and alignment, but you also want to make sure that the buildings are leaning in the same direction. And that itself is a big, big problem that it's mostly unsolved if you want to do that at scale and really, really quickly. I said earlier that there are multiple definitions of what ARD is, and I'm gonna briefly talk about what CEOS is doing. And again, there are other standards, for example, from IEEE doing ARD. So don't get stuck on this specific example, but I just want to show you, for example, what are the two extremes and why ARD doesn't fit, or our idea of ARD doesn't fit in many of those standards. If you get the specification for CEOS, they will be talking very, very heavily about calibration, traceability, surface reflectance, accuracy, and uncertainty. And which is pretty much what I talked about earlier about surface reflectance. So most of the ARD specification focus only on surface reflectance and very accurate surface reflectance. What I show you with those building in different directions shows you that surface reflectance is only one of the many components that you need to be taken care of. And I want to show you like two extreme cases where you are in this line here where there is no calibration and you have like very accurate surface reflectance, and how those two extremes don't fit in what we are trying to do. For example, let's say that you have no calibration at all. So your satellite are, yeah, they're on focus, but the spectral information is not accurate. And I want to push this even further. You only have one band. You only have one panchromatic band, like, for example, WorldView 1 or any of the panchromatic band of the WorldView satellites. You can still apply machine learning. You can still do like a car counting here, or you can still detect airplanes. So to that very, very big extreme, you don't need calibration to do this specific task or car counting. And I'm kind to be very provocative on this. You always want to have very accurate data, but very accurate data might not always be necessary for specific tasks. And I will show you the extreme opposite of that. So even if your data is very, very accurate in surface reflectance, there is still BRDF. And I briefly touched about BRDF earlier. It depends on the viewing angles. Your object will be darker or brighter depending on the geometry. This is an image that was acquired a few days apart, but from completely different view angles. The sun was pretty much in the same position, but the viewing conditions were different. And what you can see is that this building here was brighter in this scene and darker in this one. But this one was exactly the opposite. This was darker. No, this was brighter in this scene and darker in this other scene. So BRDF is a function of the material and the roughness of the material. And so within the scene, you can have completely different BRDF behaviors. And so you want to make sure that you account for that. At the same time, I'm an advocate of not removing BRDF effects from an image because you can use that information to extract additional information. For example, this is a building, right? And this is the roof of a building. What this BRDF plot is telling me is that this material is most likely metal. And the reason is because I can see the range in reflectance going from 30 to 60% reflectance. There's a like a mirror behavior that you generally see in metals. And I also see two different lobes here, also here and here. So that means that the roof is pitched. It's not flat. So again, using BRDF, you can understand this type of behavior. But what I was saying earlier is that even if you're very accurate in surface reflectance, you still have very big variations, again, from 30 to 60%, just because of the material and its roughness. So it's really important that you account for that. So bottom line is that there is no one-size-fits-all solution. So everyone is trying to work on ARD. I think the ARD is far, far away from being solved. Maybe something more on the line of application-ready data could be better or more appropriate, maybe. Why application, no analysis? The reason is that there are many different users, and we need to recognize that users are different, and so their needs are different. For example, in agriculture, maritime, generally people are really knowledgeable of the data. They really want very accurate, calibrated, you know, all the spectral bands possible because they want to do like crop analysis, for example. And so for those users, you need to have the highest quality. For other users, for example, insurance or finance, they don't really care if the data is calibrated. They only want to know, for example, if their roof is damaged or not, or if you have a tree next to your house, because if there is a wind, maybe that tree will fall on your roof and break it. And so they have to pay damages. So that context, they don't really need to know what is the calibration. They don't care about uncertainty. They probably don't even understand uncertainty. So as providers, we need to realize how important is the end goal of what the users are trying to do. And again, there are different markets. There is a civil government, industry, intelligence. Those users have different missions, timelines, requirements, also skill set. So those are, for example, key characteristics for data sets, right? So someone might be focused on quality. Other people might be interested more in availability. Let's say, for example, there is a flood event. When there's a flood, generally there's a flood because it's been raining a lot. So there are a lot of clouds in the area. So the images collecting from a satellite, at least from an optical satellite, are not going to be good because they're going to see, you know, a lot of clouds. There might be a lot of shade, shadows. So, but it's really important to see where the flood is. And so quality is not as important. It's more the availability that is important. If you are, for example, on the ground, try to rescue people from a fire, maybe, accessibility of the data is more important. I want to be able to access the data on my phone. I don't really want to have a big server where, you know, I need to download the data, put together my Python script to extract some shape where the fire is. I don't have time to do that. And so the accessibility of the data on my smartphone is more important than anything else. And for other users, interoperability is more important. For example, I'm studying that field and how that crop developed through the summer, for example. And you know, you can get one image from WorldView 2 today and one image from Legion tomorrow, and let's say maybe a Sentinel in 2 days and maybe a Landsat in 5 days. How do you put all that data together in a way that's interoperable? So for some users, that is way more important than being able to access that data on their cell phone. And I just have 4 or 5 more slides where I just want to show you some use cases. So for example, in this case, the users found much benefit to use ACOMP, which is our atmospheric compensation software. And how they use it was to port models that were developed from on a region to another region, so image to image. And they were able to extract features like road or buildings. And this is a very important application for telecommunication providers, where they want to know if there are, for example, building, or for example, if there are like people living there. And also like as important implication for insurance, for example, for wild risk, and for example, again, if you have a tree next to your house, that's important to know if you have a lot of vegetation, for example. And so consistency of data was really, really important for this specific use case. In this other case, alignment was really important because we have a time series of data and we want to see deforestation. And so, and this is a hill, like a mountain. So also the DSM, it's very different. So if you collect from different view angle, if you don't align the data, the same tree might be here, might be here on different images. And so alignment is also really important for application, again, as deforestation or also like crop analysis. This is another example where we try to extract road network, and you know, 1 image or 2 images, we were getting okay results. If you put together, when we put together a deep stack of data, we were able to extract the entire road network in a much reliable way. And think about this, for example, if you have very narrow roads with buildings or trees, and you're looking only from this direction, that building or that tree will be occluding the road, so you won't be able to see it. Whereas if you can see the same road from multiple directions, then you'll be able to extract that road network a lot more reliably. And so if you put those 3 concepts together that I just talked about, ACOMP, the alignment, and the deep stack of images, you get what a definition of ARD is. Again, this is our definition. And once you put all those together, you can do, for example, border monitoring, or you can train data for machine learning applications. And again, this specific use case is what Manny will be talking about in the second part of this presentation, actually in the third part, after me there is Pete. This is my last slide. I think I'm doing pretty good on time. I really like this slide because it really shows the difference between imagery, information, and insight, which is something often is overlooked and not very well understood. Imagery. If I just give you this, you will probably tell me, yeah, that's probably a parking lot. And yeah, it is a parking lot. And those are cars, right? So what? What do you do with that? I don't know, it's a parking lot. Okay, let's go home. End of story. You cannot really apply that type of information to anything. But if you say, okay, this is an image of a parking lot, cool. I have a model that can detect and count all the cars in this parking lot. Okay, now it's a piece of information. I know how many cars are in that parking lot, which, maybe you're not going to do anything with that, but you can do that on a global scale and count the cars of every parking lot in front of grocery stores, for example, or any other store that you would like to track. Now, if you put together the database, now you range from information to insights, where, okay, now you know how much traffic is going through the parking lot. And let's say, for example, this is the production line of Tesla or Hyundai or Ford or whatever you want to track. You can see how many cars are producing and how many cars are pushing out to the market. Based on this information, you can have the insight about stock prediction, for example. So this is a very basic example, but shows you how you can go from just imagery, just pixels, to something that has a value and can be sold in the market.